Now, first we will discuss about the Kirchoff's law. This Kirchoff's law is very useful for dealing of the problem related to capacitors. The first is the first law, or it is also called Kirchoff junctions law. Junction or node law. Sometimes it is also known as Kirchoff current law or KCL. So, what is this? According to this law, at any junction, first meaning of Kirchoff current law, at a junction total incoming current is equal to total outgoing current. But how that law we can use in the capacitor circuit? Let for example, let these are the certain capacitor, let 3 capacitors, and these 3 capacitors are connected like this, and along with this let we are connecting certain batteries also like this. Let S1 and S2 are the 2 switches, and EMF of this cell is your E1 and this is your E2, and these capacitors have capacitance C1, C2 and C3. For example, initially switch S1 and S2 are open. At that time, let these capacitor having certain charge, we can assume like this Q1, Q2, Q3. Okay. So, these are the initial charge on a capacitor C1. C1 capacitor your Q1 charge, capacitor of capacitance C2 having charge Q2, and capacitor of capacitance C3 having charge Q3. These all 3 capacitors are connected with the cell of EMF E1, E2 along with the key. Now when switch is closed, then what will happen? So, this is the diagram. We can say before closing switch, before closing switch. Now, when switch is closed, then see the in that situation what is the charge distribution. When we have closed the switch, see after closing switch, after closing switch, see the effect. After closing switch S1, S2, this cell have EMF E1. It means potential difference between this and this your E1. So, this at higher potential, so that will create some potential difference. Means this cell and this cell, both of the cell are showing their own effect on the circuit, or these cell are start changing the potential difference which was earlier across the capacitor. So, because of the presence of these 2 cells, that cell is your changing the potential difference in these 3 capacitor. So, to neutralize that potential difference, so what will happen? Charge distribution on a capacitor start changing. So, finally, the flow of charge will stop. So, during, let this is called after closing stage, means after means final stage, final charge distribution, the final charge distribution. In the final charge distribution, some of the plate can change their polarity also. So, we cannot say that final distribution of charge means the polarity of the charges will remain same. It may change also or it may not change. So, let This capacitor have final charge your Q1 dash, and this is your Q2 dash, and this is your Q3 dash. So polarity of some of the plate may change or some may not change, that depending on the how the effect of E1 and E2 in the circuit. Now, what is the Kirchoff first law? According to the Kirchoff first law, in an isolated system, we can write here, according to first law of Kirchoff, in an isolated system, sum of the charge of a system remain constant. Okay. According to the first law of Kirchoff, in an isolated system, sum of the charge of a system remain constant. That is also called your conservation of charge. Okay. So isolated system means that part of the conductor which are not connected to any other system. See here, if we are looking these three plates, 1, 2, 3, these three plates are connected together only. These are not connected to any other external system. So that three plates can be taken as a isolated system like this. See, if these three can be taken as an isolated system. So after closing the switch S1, S2, when E1 and E2 effect will be there, that E1 and E2 effect can change the redistribution of charge, but since these three plates connected together, so whatever charge may flow between these three, that will flow only in these three plates. So charge distribution may take place, but some of the charge will remain constant. See, initial charge we can say here on the C1 plate Q1, and here your minus Q2, and on the C3 capacitor plus Q3. This is the initial charge is equal to final charge. See here, same three plates. If we are considering same three plates, see the distribution. Here plus Q1 dash, minus Q2 dash, plus Q3 dash. So this is your plus Q1 dash, minus Q2 dash, plus Q3 dash. So this is the equation we are getting by using first law of Kirchoff. So initial charge of a system is equal to your, so this is nothing, initial charge of a system, and this is your final charge of the same isolated system. This is your final charge of same isolated system. So this is called conservation of charge or first law of Kirchoff. See, one more interesting point here, same relation or same thing we can use in the another way also. Important point here, as we know, battery is not a source of charge. That concept also we can use. Cell or battery is not a source of charge. Then what battery does? It maintains the flow of charge. It only maintains the flow of charge. Cell or battery is not a source of charge. It only maintains the flow of charge when or till electrical equilibrium is not established. Till electrical equilibrium not established. Okay. So meaning of this statement is this: initial charge was your Q1, Q2 and Q3 on these three capacitors. At that time our switches was open, and when the switches close, then the charge is your Q1 dash, Q2 dash, Q3 dash. So why the charge distribution took place? The charge distribution took place because of these cells. So when the switch S has closed or S1, S2 has been closed, so this cell has created certain potential difference, and because of that charge start flowing. So once again, as the cell or battery is not a source of charge, it only maintains the flow of charge till electrical equilibrium not established. It means we can say whatever charge enter from one of the electrode of the cell, same amount of charge has to leave from the cell, other electrode. So amount of charge leaving from this electrode will be same as the amount of charge coming to the another electrode. So that charge we can equate, then also we can get the same type of relation. How can we equate? See, if I am looking this plate, whatever charge coming from this electrode, that will go only on this plate after closing the switch S1, S2. The final charge on this plate is your minus Q3 dash, and initial charge was your minus Q3. So how much charge has flown? The amount of charge has flown means final charge minus initial charge. The final charge we can say delta Q is equal to final charge your minus Q3 dash minus of initial charge your minus Q3. So delta Q is nothing, Q3 minus Q3 dash. This is the amount of charge has flown through the lower potential terminal of a cell after closing switches S1 and S2. Now see here, how much charge will come here? Whatever charge coming here, that charge can come from this part as well as from this part. See how much charge will come from this part? See here. If I am looking this plate final charge is your Q2 dash and initial charge your Q2. So how much charge came in this side? Final minus initial, Q2 dash minus Q2. Then how much will go in this side? Just opposite to that. So that will be your Q2 dash minus Q2. Okay. See here, final minus initial in that side, finally your Q2 dash minus Q2. How much will go here? So this will be your Q2 minus Q2 dash. Now, so this is the amount of charge coming from this side, Q2 minus Q2 dash. Similarly, see here, charge is your minus Q1 dash final and initial your minus Q1. The final minus initial your minus Q1 dash minus plus the Q1 minus Q1 dash. In that side it will be your Q1 dash minus Q1. So this much charge is coming here. The total charge coming here, we can include these two or we can add. The total charge is this and this is charge. Again we can write. So how much charge is coming here? Q2 minus Q2 dash plus Q1 dash minus Q1, and amount of charge leaving Q3 minus Q3 dash. Now see, we can bring dash term one side and another term like this. So from here we can get Q1 dash minus Q2 dash plus Q3 dash is equal to your Q1 minus Q2 plus Q3, and this equation and this equation are the same equation. So there are two ways of solving or applying the conservation of charge rule. One way is that we can select any isolated plates and the sum of the charge on those isolated plates before closing switch and after closing switch must be the same as we did here. Or another thing is that, as we know, cell is not a source of charge. Whatever charge enter from one of the electrode of a cell, same charge has to leave from the other electrode. So just calculate how much charge is entering from one of the electrode and then equate it with the how much charge is leaving from the other electrode. So this is the another concept of Kirchoff first law. Now come to the second law of Kirchoff. Second law of Kirchoff. Kirchoff's second law. This is also called your KVL or Kirchoff's voltage law. KVL, as well as it is also known as or Kirchoff's loop law. So all are the same meaning of same term, Kirchoff's second law. First point, it is based on conservation of energy. It is based on conservation of energy, and in general form we can write, see, according to this law, it means that is the meaning of application point of view, how we are applying the Kirchoff's second law. According to this law, sum of potential drop in a loop, in all electrical elements will be zero. Okay. It is based on conservation of energy. First of all, according to this law, sum of potential drop in a loop in all electrical elements will be zero. See the meaning of this statement, then you can get clear idea of this Kirchoff second law. Let we are having two capacitors and these two are connected with a cell. E is the EMF of the cell and C1 and C2 are the capacitance of a capacitors. Initially switch S was open and capacitor does not have any charge. Now how to apply Kirchoff's second law? See, when switch is closed, as soon as switch is closed, It means what I did, I connect a higher potential terminal of a cell with this plate and lower potential terminal of a cell with this plate. Because of this connection, flow of charge took place. As we know, charge starts flowing from lower potential, it means electrons, lower potential to higher potential. So when electrons start moving from this plate to this plate, so this plate here become positively charged. So we can have, let Q is the charge on this plate, and if here minus Q charge came on this plate, from where that minus Q can come? These two plates are connected together. So on these two plates, initial charge was 0. Right now charge here minus Q. It means that charge has come from this plate. So this plate you are having charge plus Q, like this. So this is the final distribution of charge. So that charge is the final charge, means when the electrical equilibrium established. Electrical equilibrium established means that this plate and this electrode are at same potential. This electrode and this electrode is also at same potential. That's why the further flow of charge stop. Now, how to use conservation of energy? According to conservation of energy means initial energy is equal to your final energy. So what is the initial energy? Initial energy means before closing switches, that was your 0 here because there was no charge on the capacitor. Now final energy. Final energy means energy is stored in this capacitor. So how much energy is stored on this capacitor? Half Q square by C1. On this capacitor, half Q square by C2. This is the energy stored. And when energy is storing, so from where? What is the source of that energy? Source of energy, your cell. The battery is supplying energy. How much energy is supplied by the battery? That we can say Q into EMF and plus heat. Actually, this is the meaning of conservation of energy. So whatever the work done by the battery, from here we can say work done by the battery or QE is equal to your half Q square by C1 plus half Q square by C2 plus heat. This is the meaning of conservation of energy. So here initially there was no energy. So what is the source of energy? Source of energy was the battery, and whatever energy is supplied by the battery, where that will go? Some part of the energy is stored in the capacitor, and during the charging of a capacitor, since charge is flowing, so when charge is flowing, so there is some loss of energy in the form of heat. So loss of energy in the form of heat is this, and energy stored in the capacitor is this. So in general we can write, from energy conservation, initial energy is stored in capacitors. In capacitors, that we can represent UI plus energy supplied and sometime your absorb. When supply positive, absorb by cell. Absorb means sometime suppose two cells are there. Some of the cell are giving energy into system some of the cell may be taking energy to the system. So, initial energy is stored in the capacitor Ui plus energy supplied positive or absorbed by cell is equal to your final energy stored in capacitor, final energy is stored in capacitors. This we can say U final plus heat. So, this is the conservation of energy, and we can say second law of Kirchoff. And how to calculate energy supplied or absorbed by a cell? So, that we can calculate by the work done by cell. Energy supplied or absorbed by cell is equal to Q into EMF, where Q is charge passes through cell. Charge passes through cell. Q is the charge passes through cell, and E is the EMF of the cell. In this manner we can calculate. So, this is the meaning of based on conservation of energy. But all the time it is not possible to make all this type of calculation. We can use the Kirchoff's second law according to this rule. That is the another form of representing Kirchoff's second law. Sum of the potential drop in a loop in all electrical elements. So, for sum of the potential drop, so we can move from one point to another point in a loop. We are starting from here. For that we must know the sign convention. Sign convention are same as we did earlier. When we are leaving the cell or any capacitor with a lower potential terminal of a capacitor plate or lower potential terminal of a cell, then we have to use the negative, and when we are leaving the higher potential terminal of a cell, then positive. See, as we are applying Kirchoff second law here, we are starting from this point and come back to the same point. So, when we are going to this plate, this capacitor, so since we are leaving from the negatively charged plate, so write the potential of capacitor negative, and that is written as Q by C1. Then we are leaving from the another plate of capacitor, that is also negatively charged, Q by C2. Then we are leaving the cell with a higher potential E. This is the equation we can make by using a Kirchoff second law. Similarly, if we are considering any other example, for another example, let this type of distribution or capacitors are given. These are two loops are given here, E1, E2 are the cells, C1, C2, C3 are three capacitors and their capacitance. Let here charge Q1, here charge at Q2, and let here charge is your Q3. Now if you want to use Kirchoff second law here, you can select first a loop. If I am selecting, this is the first loop. So, first select the loop as well as direction in which you want to go on that loop, and let this be your second loop. Second loop. Now see, if we are leaving from here and coming back to the same place, see, if I am starting from here, I will go here first. Then when we are leaving through the capacitors of capacitance C1, we are leaving with a negatively charged plate. So, potential of that is minus Q1 by C1. Then we are leaving with this plate minus Q2 by C2, then here plus E1, which is equal to your 0. This is the meaning of that, sum of the potential drop. So, sum of the potential drop we took in all electrical elements in a loop, and that is equal to your 0. If I am using the second loop, see, if I am starting from here, first I am leaving this plate, this capacitor, and we are leaving with a positively charged plate Q3 by C3, then with a lower potential terminal minus E2, then we are leaving minus Q2 by C2. This is one more interesting point here. It does not mean the Kirchoff's second law is applicable for a loop only. You can apply Kirchoff's second law between any 2 points. Let for example, suppose this is a point A, this is point B, and if we want to use Kirchoff's second law between any 2 points, so you can apply like this. The first, assume a potential of that point, define the potential of those 2 points across which you want to apply Kirchoff's second law, that VA and VB. Now, you can follow any of the path, either you can go from A to B by this way, or you can go like this also, no problem. Suppose you are moving like this path. So, if we are starting from A, the first write the potential of point A as a VA, then follow the same rule. Now, we are leaving with a negatively charged plate. So, minus Q1 by C1, then we are leaving from positively or higher potential terminal of a cell plus E2, then we are leaving with a negatively charged plate minus Q3 by C3. And now, when we are reaching at B, so either you can write equal to VB or minus VB is equal to 0. This is the one way. Same thing you can do if you are following this path. If we are following this path, then start from A, VA, then here minus E1, then you are reaching at B is equal to your VB like this. So, you can apply Kirchoff's second law across any 2 points as well as in a loop also, and if you are following in a loop, you can go either clockwise or anti-clockwise, doesn't matter. So, these are the 2 Kirchoff's law. With the help of these 2 Kirchoff law, you will be able to solve almost 90% problem related to charge distribution in a capacitor. See one by one certain examples.